Okay, so in today's class we are starting with counters based on shift registers. Here, before that we have already studied about the counters. Counters, counter is a pattern generator. It generates different pattern sequences. It may be a binary counter, it may be a non-binary counter, right? So here, we will be studying some of the counters based on the shifting operations. So what is this? This is a mod 4 ring counter. Okay, ring counter means initially it will be set to one of the flip flop will be set to 1, all other flip flops will be set to 0. Okay, so here you can see here this QA is set to 1, QB, QC, QD is set to 0, right? So here the QD output is connected back as an input to the leftmost flip flop. Okay, that is this flip flop. Flip flop 1, flip flop 2, flip flop 3 and flip flop 4. Right? How many flip flops are there? 4 flip flops are there. Okay, it is a D type of flip flop. Now, how does it count? How does this ring counter count? Initially, what we have to do is we have to set one of the output of the flip flop as 1, all others as 0. Okay. So now here, by seeing this logic diagram, we can see that the QD, that is the last flip flop output, is connected back as an input to the first flip flop, that is QA. So upon the occurrence of the count pulses on the clock, what happens? This QD shift backs to QA, right? What is QD here? Upon the occurrence of the clock, this QD, this 0 will come and sit in the QA. Next, this one will shifted, QA will be shifted to QB. QB is 0. This QB is shifted to QC. Next QC is 0 here. This QC is shifted to QD. Right? So shift operations. What happens? This QD is connected back as an input to this. QA is shifted to QB. QB is shifted to QC. QC is shifted to QD upon the occurrence of the clock. These are positive edge triggered D flip flop. Okay. So as I have already told you, a ring counter is a circular shift resistor which is initialized so that only one of the output of the flip flop is in the 1 state and all of the flip flops are in the 0 state. Upon the occurrence of the each count pulse, a single one is shifted into the adjacent flip flop. As a consequence, we have n bit flip flop for the n bit states. How many flip flops are there? See here, 1, 2, 3, 4. So here how many states are there? 1, 2, 3 and 4. N bit flip flop generates n states. Okay, you can see here 1. So what I will write here for just for a reference, first one of the output, that is QA, QB, QC, QD. This QD is 0, no? This QD is connected back as an input to this first flip flop. So here what happens? This is shifted here, so 0 will come. This 1 will shift here, so 1 will come. This 0 will shift here, 0 will come. This 0 will shift here, 0 will come. Next again QD is shifted. Okay, QD will come here. QA will be shifted to QB. QB will be shifted to QC. QC will be shifted to QD. Next again QD is connected back as an input to QA. So this 0 will come here. This 0 QA will be shifted to QB. QB will be shifted to QC. QC will be shifted to QD. Next so this is 1. Okay, this one is here. Next this one will shift here. 1. This 0 will come here. This 0 will come here. This 0 will come here. Okay, so it is repeated now. 1 0 0 0. Earlier it was 1 0 0 0. So how many state? State 1, state 2, state 3, state 4. Right? So you can see here this one. It has 4 different states and it has 4 flip flops. 4 flip flops means n bit flip flop ring counter generates n status. Ring counter. It is not efficient in the number of flip flops used, but provides a decoded output. If I want to detect any particular state in the counting sequence, it is only necessary to interrogate the output of a single flip-flop. Suppose if I want to detect if the counter is in this state, I want to detect that this is in this state. So what I have to do? I have to interrogate it means I have to detect that only QA output, whether it is 1. If it is 1, then all others will be obviously 0, right? So in order to detect any state, I have to check only one of the flip-flops. But it is not efficient because n flip-flop will generate n states. So it is not efficient. But in order to detect the output, only one of the output of the flip-flop should be detected to check whether which state it is. Okay. So this is about the ring counter. So here one more type is mod 8 twisted ring counter. This is logic diagram, this is a counting sequence. Okay, here we have the counting sequence. Here instead of QD, okay, QD bar is connected here as an input. Okay, see here the clocks are applied simultaneously. The first you check about the clocks are applied simultaneously, it is a synchronous type. Okay, next see clocks over, next D flip flop. First you draw this D flip flop 1 2 3 4. I'm talking about the construction. 1 2 3 4 flip flops you draw and give the inputs like D. Okay, and then the outputs Q bar, QA, QB, QC, QD. Okay, you can take the wire connected from QA, QB, QC, QD. Okay. Next, Q bar is connected to as an input to this. So what happens? Initially all will be 0. Let me tell you here by writing. So initially all will be 0. Initially these are assumed to be 0. All the outputs are assumed to be 0. In the ring counter we had connected QD as an input to the D. Here we are connecting QD bar. What we are connecting here? QD bar we are connecting as an input to this, the first flip-flop, right? So QD bar is what now? 1. If QD is 0, QD bar will be 1. Okay, so next upon the occurrence of the clock it will shift. This 0 here, this 0 here. Next QD bar. QD is 0, QD bar will be 1. Okay, so this one will shift, this 0 will shift, this 0 will shift. Next QD is 0, QD bar will be 1. This one will shift, this one will shift, this 0 will shift. Next this 0, QD is 0, QD bar will be 1. 1, okay, 1. This one here, this one here. QD bar, this QD is 1, QD bar will be 0. 0 will shift here. This one will come here, this one will come, this one will come. Next.
Excuse me, ma'am.
Yes, 1 minute.
Sorry for the disturbance, ma'am. Some students may want.
So QA, QB, QC and QD. Initially all are 0. Okay. QD bar is connected. So QD bar is connected as an input to the first flip-flop. QD is 0. QD bar means 1. So this 0 will be shifted to QA upon the occurrence of the clock. Next QA is shifted to QB. QB is shifted to QC. QC is shifted to QD. Because of this wire here, you can see this. So this 0 will come here, this 0 will come here, this 0 will come here. Okay. Next QD is 0, so QD bar will be 1. That will be shifted to QA. This 1 is shifted here, this 0 is shifted here, this 0 is shifted here. Next QD is 0, so QD bar will be 1. Okay, 1. Here this one and then this 0. Next QD is 0, QD bar will be 1. Okay, 1, this 0, QD is 0, QD bar will be 1. So here it will come here. This one will shift here, this one will shift here, this one will shift here. Now QD is 1, QD bar will be 0. So it will be shifted to QA. This one will come here, this one will come here, this one will come here. QD is 1, QD bar will be 0. QA will be shifted to QB, QB will be shifted to QC, QC will be shifted to QD. Next, Here again QD is 1, QD bar will be 0. So this 0 will come here, this 0 will come here, this 1 will come here. Next this 1, QD is 1, QD bar will be 0. Okay. So 0, this 0, this 0, this 0. So these many different states are there. 0, 0, 0. It returned back to 0, 0, 0, no? So first initially all were 0. So you have to count the sequence until it will get the 0, 0, 0 back. Okay. So here how many states? 1, 2, 3, 4, 5, 6, 7, 8. So here the twisted ring counter, the complement of the rightmost flip-flop serves as input to the leftmost flip-flop. 2n states occur in the counting sequence of an n stage counter. What is it telling is if we have n flip-flops, we can generate 2n states in this twisted ring counter. What is this known as? This is a twisted ring counter. In a ring counter, what happened? I'll show you the slide. In ring counter, we connected QD directly as an input to the D. Whereas in the twisted ring counter, what did we do? Instead of QD bar we have connected. This is the only difference. And in ring counter for n flip-flop, we had n states generated. Whereas in twisted ring counter for n flip-flop, we are generating 2n states. Okay, if we have 4, if suppose in this counter only we have 4 flip-flops. 2 into 4, how many? 2 into 4 we are getting 8 states, right? So we have 1 to 8 states. So for 4 flip-flops we have 8 states. That means in general for n flip-flop we have 2n states. Next, talking about the counters based on shift register continued. This is again mod 7 twisted ring counter. Here twisted ring counter for odd number of states. That is, in the previous slide we studied that for 4 flip-flops we have 8 states, right? 2n states, even number of states. Mod 7 means mod is the total number of states. How many states we have? 7 states. So here what happened, the change is QD bar and QC bar are connected to AND gate and then given as an input to the D input of the first flip-flop. Okay, this is twisted ring counter for odd number of states. The state consisting of all ones is eliminated from the counting sequence. That means if all are 1, 1, 1, that state is eliminated from the sequence by using this QC, QD bar. Let us see from the counting sequence. Okay, achieved by connecting QC bar, QD bar to the input of the leftmost T flip-flop. How do we eliminate the 1, 1, 1 sequence? How do we eliminate the 1, 1, 1 sequence? 1, 1, 1. This sequence is eliminated by twisted ring counter with mod 7 twisted ring counter. How we have eliminated? By connecting QC bar and QD bar, take a AND gate and then connect back to the input of the first flip-flop. Okay, each state is detected by using of a single 2 input AND gate. Okay, so now I will talk about this QA, QB, QC, QD, 0, 0, 0, 0. Okay, so here QC bar, QD bar both are 1. Okay, QC, QD is 0, 0 means here it will be 1, 1, isn't it? So this one will go here, this one will go here, output will be 1. So that will be gone to this first flip-flop, 1 will come. Next again it will shift. Okay, now again both are 0, 0. So 0, 0 means 0, 0 means QC, QD 0, 0. QC bar, QD bar are 1, 1. So that 1, 1 is given as an input to this AND gate. 1 will go here. So here it will get 1 again. 1, 0, 0, 0. Again both are 0. 1 I will get 1, 1, 0. Right? So similarly we have 0, 0, 0, 0. 1, 0, 0, 0, 1, 1, 0, 0. Both are 0 means we'll get 1. Here 1. Here this one will go. This one will go here. This 0 will go here. So 1 and 0 I will get 0. 0 will go here, 1 will come here, 1 will come again, 1 will come here. Like 1 and 1. So both will be 0. 0 will come here, 0 will come, 1 will come here, 1 will come here. Both are 1 means QC QD 1 means QC QD bar is 0 0. 0 and 0 I will get 0 again, 0 0 0. This one will shift here. 0 1. So QC bar will be 1, QD bar will be 0. 1 and 0 I will get 0 only, 0 0 0 0. Okay. So how many states I have here? 1 2 3 4 5 6 7. So mod 7 twisted counter, we have eliminated 1 1 1 1 state. So we have 7 different states in this particular type of counter based on the shift registers. Okay, so here we have eliminated 1 1 1 1 by using the 2 input AND gate by connecting QC bar and QD bar. You can see here QC bar and QD bar are both connected as an input to the AND gate. Output of the AND gate is connected as an input to the first flip flop. Okay. Design of a synchronous mod 6 counter using clocked JK flip flops. We are using here positive edge triggered JK flip flops. Okay, so mod 6 counter means it will count 6 different states. This is a general structure of a synchronous mod 6 counter using positive edge triggered JK flip flops. Okay, so you can see here this is the first flip flop, this is the second flip flop, this is the third flip flop. Okay, so we have here so flip flop 2, flip flop 3. Okay, so this is the first flip flop, this is second flip flop, this is the third flip flop. Obviously it has J1 K1, J2 K2, J3 K3 as inputs to the flip flop respectively. Next Q1 Q1 bar, Q2 Q2 bar, Q3 and Q3 bar. These all are connected to this logic network. Okay, this logic network we need to design this logic network. These flip-flop inputs and outputs are connected to the logic network. This design we need to do by constructing the application table, excitation table, state table. Okay, so how do we construct those? Okay, we can see here. Okay, and one more thing, this is a synchronous mod counter. Why the synchronous? You can see the C clock. Clock is connected synchronously at a time it is applied to the flip-flop. Okay, these are count pulses. This clock is applied simultaneously at a time, hence it is known as a synchronous. So let us study the design of a mod 6 counter, synchronous mod 6 counter using positive edge triggered JK flip-flop. So what is this, students? This is a general structure of a synchronous mod 6 counter using the positive edge triggered JK flip-flops. Okay, so here students, this one I just for the reference, before I start the design, you should know the next state table, you should also know the application table. Now let me teach you next state table. I have already taught you while the topic solving characteristic equations. We have all written the next state table. So once again for your reference, okay. So here 0 0 0 0, JK is 0 0, present state may be 0 or 1. JK is 0 1, present state may be 0 or 1. JK is 1 0 1 0, present state may be 0 or 1. JK is 1 1 1 1, present state is 0 1. Okay. Here what you have to do, whenever JK is 0 0, it will retain the present state. Q is 0, Q plus is 0. Next, whenever JK is 0 0, present state is 1, it will retain the present state 1 1. Next, whenever J is 0, K is 1, it is in the reset state. Present state is 0, but whenever J is 0, K is 1, it will be in the reset state 0 0 1, present state may be 1, but it will be in the reset state. Whenever J is 0, K is 1, it will be in the reset state, 0 state. Next, J is 1, K is 0, J is 1, K is 0. Okay, so it will be the set state. Set state means 1, 1. Next, whenever j is 1, k is 1, it will toggle. So present state is 0, next state will be 1. So present state is 1, next state will be 0. Okay, so this is how you have to write the next state table. From the next state table, how to write the application table? Now it is reverse. Q plus may be 0, 0, maybe 0, 1, maybe 1, 0, maybe 1, 1. What are the inputs for the Q plus? Now let me check for 0, 0. So here it is 0, 0, first row and the third row. For this, what is the j? J is 0. So I have written 0. What is k? K is 0 and 1. So I have written 0, 1, no? So don't care, dash. J, k is 0 also, 1 also. So dash. Next, q is 0, q plus is 1, 0, 1. Where are the rows? I have to search. Where it is 0, 1? Here it is 0, 1. Isn't it? And here it is 0, 1. What is j? J is 1. J is 1 here also and here also. I have written j as 1. K is 0 and 1. K is both 0 and 1. So I have written don't care. Next 1, 0. I have to search 1, 0. Where is 1, 0? Here. Next 1, 0. Where it is? Here. So j is 0 and 1 also. 0 and 1 also means dash. K is here 1 and 1. So 1. Next both are 1, 1. Here this row and this row. Here it is 0, 1. J is 0. This one 1, 1 no. J is 0 here. And here 1, 1. J is 1. J is 0 and 1. So don't care. Next K is 0 here. Next here K is also 0. So I have written 0. So this is how we have to write the application table from the next state table. Did you understand this? Design a mod 6 counter using positive edge triggered JK flip-flop for the following given counting sequence. Okay. So here I have given a sequence 0. After 0 it should go to 2. After 2 it should go to 3. After 3 it should go to 6. After 6 it should go to 5. After 5 it should go to 1 and then again 0. How many states? 1, 2, 3, 4, 5, 6. 6 states are there, isn't it? So it is a mod 6 counter here. Okay. So 6 states are there. So it is mod 6 counter. So I will write here now. First state is 0, 0, 0. Next state is 2. 0, 1, 0. Next state is 3. Next state is 6. Next state is 5. Next state is 1. Okay. So in this way we have to write this. Okay. So after 0 what we have? 2 we have. So write 2 here. For this 0, 2. So for 2 what is the next state? 3. For 3 what is the next state? 6. So for 5 for 6 what is the next state? 5. For 5 what is the next state? 1. For 1 what is the next state? 0. So did you understand this? How to write this?